In this video, we're going to show that the sum of two continuous functions is also continuous. So I've written our task up here. If f of x and g of x are both continuous at some x value a, then we want to show that their sum, f plus g of x, is also continuous at that same x value a. And by the definition of continuity, that means our goal is to prove that the limit as x approaches a of f plus g of x is equal to the function value at a, f plus g of a. Informally, what we expect to get based on the nearby behavior is exactly what we do get. Of course, in proving a limit, we're going to use the epsilon delta definition. So this means that given an epsilon bigger than 0, given a positive number, which will be a standard of closeness for how close we want the y values on the graph of f plus g to get to the number that is our limit, f plus g at a, we're going to be able to find a delta bigger than 0. That's going to be a standard of closeness for our x values, so that if x is close to a without equaling a, then the distance between f plus g of x and f plus g of a will be smaller than this number epsilon. Notice that there are two if-then statements in here. Our overall goal is to prove that if f and g are continuous, then f plus g is continuous. For that, we're going to suppose that f and g are continuous at a and try to show that f plus g is continuous at a. In doing that, we have to prove that this limit is true, and so that involves another if-then. So there's going to be an if-then inside of an if-then. I'm going to just explore a little bit what this ultimate goal looks like. Let's remember how we evaluate a sum of two functions. So this quantity that I have in absolute values starts out with f plus g of x. We evaluate the sum of two functions pointwise. So all that means is that we plug in x to f and g and then add the results. Same thing for what we're subtracting here. We're subtracting f plus g of a, so that would be f of a plus g of a. Notice I was very careful here to put that in parentheses because I'm subtracting the whole thing. I'm going to go ahead and distribute that negative. So this is absolute value of f of x plus g of x minus f of a minus g of a. This is the thing that I want to make smaller than epsilon. Inside the absolute value here, I'm just going to change the order of those two terms. So I'll be able to say this is the absolute value of f of x minus f of a plus g of x minus g of a. And here I have four terms inside the absolute value, but I'm going to think of it as two parts. I've got the f part and the g part. And I'm going to use the triangle inequality to say that this is less than or equal to the sum of the absolute values of those two parts. So the absolute value of f of x minus f of a plus the absolute value of g of x minus g of a. Let's just make a note that this was by our triangle inequality. Now, ultimately, this is what I'm going to try to make less than epsilon. I wanted this thing to be smaller than epsilon, but if I can make this piece smaller than epsilon, it's going to follow that what I started with is also smaller than epsilon. And what's nice about this is because we're going to have supposed that f is continuous at a, we're going to know that we can control the size of this vertical distance between a y value on the graph of f of x and the y value that we get when x is a. Okay, excellent. Similarly, we're going to know that we can control this distance. So I'm going to control these two things by knowing that f and g are continuous at a. Really important point in this proof is to remember that epsilon is just a name. It's a name for this positive number, which is our standard of closeness for our function. Okay. And epsilon is the standard of closeness that I'm using for f plus g. But if that's a positive number, epsilon over 2 would also be a positive number. If I just cut it in half, I still get a positive number. And I can use that as my standard of closeness for f and for g, so that if I can make this smaller than epsilon over 2 and this smaller than epsilon over 2, then when I add them together, the sum will be smaller than epsilon. Pretty cool. All right, so let's now actually try to work with our formal proof. I have not written out all of the steps. I've just done a little bit of informal strategizing here. All right, so if I'm proving an if-then, the first thing I do is I suppose the if. So I'm going to suppose that f of x is continuous at a, and that g of x is continuous at a. Now, what it means for them to be continuous is that I know that the limit as x approaches a of f of x is equal to f of a. That's going to be rather important, so I'm going to put a star by that. And I also know that the limit as x approaches a of g of x is equal to g of a. That will also be important, so I'll put a double star by that. Okay, so I've supposed that. Now I'm ready to try to prove that this limit is valid. So for that, I'm going to need an epsilon. So let's let epsilon be a positive number. And as I said, as we were strategizing a minute ago, that means that epsilon over 2 is also a positive number. So here I have two positive numbers. This is going to be my standard of closeness for f plus g. This is going to be my standard of closeness for the two individual pieces, f and g. Okay. Now, I know that this limit is true. So by star, I know that there exists some delta, I'm going to call it delta 1 because I've got two functions here, some positive number delta 1 such that if 0 is less than the absolute value of x minus a is less than delta 1, then the absolute value of f of x minus f of a is less than epsilon over 2. I don't have to prove this because I know that this limit is true. So I can use the definition not only to prove certain limits are true, but to know that certain inequalities hold if a limit is a given value. Similarly, by double star, there exists a delta 2 bigger than 0. I don't want to assume that it's the same number for f and g, but there's some standard of closeness for my x values that works for g. So this would be such that if 0 is less than the absolute value of x minus a is less than delta 2, then the absolute value of g of x minus g of a will be less than epsilon over 2. Excellent. So I have two different, potentially different numbers, one of which controls the size of this thing, and the other of which controls the size of this thing. I want both because I'm greedy. So I'm going to let delta be the minimum, the smaller of the two, delta 1 and delta 2. So I'm claiming that this is the delta that's going to work to prove this inequality. In order to do that, of course, since this is an if-then, I need to suppose the if part. So I will suppose that 0 is less than the absolute value of x minus a is less than delta. Excellent. I'm going to now spell out what that means. The idea is this is going to give me these two pieces, which I can then put together. So let me do some erasing again. I'm going to keep this up just because I want to be able to refer back to this in just a moment. So I've just supposed this. Thus, 0 is less than the absolute value of x minus a is less than delta, which is less than or equal to delta 1. Because if delta was the smaller of these two things, if the smaller thing was delta 1, delta is equal to delta 1. If the smaller thing was delta 2, delta is smaller than delta 1. Okay. But 0 being less than the absolute value of x minus a less than delta 1 implies that the absolute value of f of x minus f of a is less than epsilon over 2. That's what we had right here. Okay. Since I'm referring back to that, let's give that a symbol. I'm going to just call that smiley face so that I don't get too many stars. Okay. Also, 0 is less than the absolute value of x minus a less than delta, but that's less than or equal to delta 2. And 0 being less than the absolute value of x minus a less than delta 2 implies that the absolute value of g of x minus g of a is smaller than epsilon over 2. And that's by this statement right here, which I'm going to call double smiley face. Excellent. So now I think we're ready to talk about what we get when we add these two pieces. Sorry, now we're ready to talk about what we're trying to show is smaller than epsilon. So, transition word, let's consider the absolute value of f plus g of x minus f plus g of a. Remember, that's what we're trying to show is smaller than epsilon. So now I'm going to be doing some of the same work I did earlier. The absolute value of f plus g of x minus f plus g of a is equal to the absolute value of f of x plus g of x minus the absolute value of f of a plus g of a. That's just the definition of how we add functions. Distributing the negative, that's the absolute value of f of x plus g of x minus f of a minus g of a. Switching the order of the terms, just to rearrange them. Again, I'm going to switch the order of these two pieces. So that's equal to the absolute value of f of x minus f of a plus g of x minus g of a. And here's where we use our triangle inequality. That's less than or equal to the absolute value of f of x minus f of a plus the absolute value of g of x minus g of a. So that was our triangle inequality. But now I can use what I've stated up here, that I know that this thing is smaller than epsilon over 2, and this thing is also smaller than epsilon over 2. So I probably want to be able to refer back to those statements. So let's just call this star smiley. Okay. So I know that this is less than or equal to, by star smiley, epsilon over 2 plus epsilon over 2, but that's just epsilon. What that shows is that thus the limit as x approaches a of f plus g of x is equal to f plus g of a, and what that shows is that f plus g of x is continuous at a, which was what we were asked to show in the beginning.